All right, let's dive into something pretty incredible. We're going to break down how a truly revolutionary AI is being built. And its job isn't just to treat patients, it's to see into their medical future, to predict dangerous, life-threatening errors before they can even happen.
So this really gets to the heart of the problem with a question that, it feels like we shouldn't even have to ask in this day and age. Why do harmful drug reactions still happen in our modern hospitals? I mean, with all the data we collect, how in the world do these things still slip through the cracks?
Well, it turns out the answer isn't about the data itself, but how we look at it. So check this out. On the left, that's the old way, a traditional patient record. It's just a flat list of facts, right? Patient 123 is on warfarin. Patient 123 is also on aspirin. Oh, and a lab result is high. To see the danger there, a doctor has to literally connect those dots in their own head. But now, look at the right. That's the medical mind map. It's not a list, it's a living network. It knows that warfarin interacts with aspirin, and it knows that interaction causes a risk of bleeding. The connection is already there, plain as day. And that is the huge shift we're talking about today.
This whole situation really highlights what you could call a massive and, frankly, a really dangerous blind spot in modern medicine.
So here's the problem in a nutshell. A patient's story isn't a single neat book. It's more like a bunch of scattered pages thrown into different filing cabinets or, different tables in a database. So the crucial link between a drug someone's taking, a specific lab test, and a potential disaster, it's often totally invisible to the software we use every day. So the real danger here isn't that we're missing the data. The danger is that we're missing the connections between the data.
So what's the fix? Well, the solution is to build what we've been calling the medical mind map.
Okay, so the fancy term for this technology is a knowledge graph. But honestly, the best way to get it is to just completely forget about spreadsheets. Instead, I want you to picture a giant, sprawling mind map of all medical knowledge. Every single piece of information, a patient, a drug, a lab result, a disease, is a single dot on this map. And the lines connecting all those dots? Those are the relationships between them. That's the magic.
So you might be wondering, how on earth do you build a map that massive? Well, it's actually pretty simple at its core. You build it one connection at a time, using this three-part statement called a triple. Think of it like a really simple sentence, a subject, a predicate, and an object. So for example, patient 123, that's the subject, takes medication, the predicate, warfarin, the object. That simple little structure, that's the Lego brick you use to build the entire thing.
Okay, so we've got our map, and we know how to draw the lines connecting the dots. But without any rules, you just have total chaos, right? And that brings us to our next big idea, writing the rulebook. And this rulebook, it has a technical name. It's called an ontology. Now, this part is absolutely critical. An ontology is basically the set of logical rules that governs the entire mind map. It defines what things even are, like this is a patient, that is a drug. And way more importantly, it defines how they're allowed to connect. It's what brings structure and really just good old common sense to all this data.
So what do these rules actually look like in practice? Well, they're surprisingly intuitive, and they sound like common sense. For instance, a rule might say that only patients can take drugs. A drug can't take another drug. That just doesn't make sense. Another rule clarifies that warfarin is a type of anticoagulant. It also makes sure the system knows that anticoagulants and antiplatelets are totally different things. But here's where it gets really powerful. The rules can also handle complex logic, like this last one. If a patient is taking two drugs that are known to interact, the system automatically tags that patient with a drug interaction risk. It does the thinking for you.
All right, we have the map, we have the rules. Now it's time to put it all together, bring this thing to life, and, as we're about to see, actually make the map think.
And I just want to pause here for a second to talk about the scale, because it's absolutely massive. We're talking about a knowledge graph with over 5 million individual connections. 5 million! Linking hundreds of thousands of patients, drugs, and diseases. So this isn't just some simple diagram you could draw on a whiteboard. It's this huge, sprawling digital brain that represents a hospital's collective knowledge.
And that, of course, leads to a very practical question. With millions and millions of connections, how in the world do you actually ask this giant mind map a question?
Well, you use a special query language called SparkQL. You can think of it as being kind of like SQL, but for graphs. Now, I know the code on the left might look a little intimidating, but the idea behind it is actually really simple. All we're doing is translating a plain English question like, hey, find me all the patients who are taking two drugs that interact with each other, into a pattern the graph can search for. And here's the cool part, the computer isn't just scanning rows in a table, it's literally tracing the paths along the connections that we built.
But this brings us to a really interesting new challenge, something that researchers call the translation problem. See, the graph sees the world in one way, as a beautiful network of relationships and connections. But our machine learning models, the AI engines that actually make predictions, they speak a totally different language. They don't understand relationships. They only understand numbers, specifically long strings of numbers called vectors. So the big question is, how do you bridge that gap?
And this is where we get one of my favorite analogies for this whole process. It's like trying to translate a family tree into a set of GPS coordinates. Think about it. The goal is to place every person on a map, and their location on that map has to represent their relationship. So siblings should end up really close together, right? While third cousins twice removed should be way far apart. The coordinates themselves are just a bunch of numbers, but hidden inside them is the entire rich structure of that family tree.
Okay, so once we've solved that translation problem, we can finally get to the real payoff. This is where we go from just having connections to making actual predictions.
And here's something absolutely critical to understand. These bad drug reactions, they don't just happen out of the blue. They're a story that unfolds over time. On day 1, a patient starts warfarin. A couple of days later, they start aspirin. And right then, the clock starts ticking on that dangerous interaction. By day 5, their lab results start to creep up, showing that the risk is getting higher. And then finally, on day 6, the bad thing happens, the bleeding event. Any AI that wants to predict this has to understand that entire sequence, not just a single snapshot in time.
And so, here's the result. This is the moment it all comes together. A standard machine learning model, using the exact same data, but just in boring old rows and columns, gets about 65% accuracy. Which, okay, that's not terrible. But the graph neural network, the GNN model that learned directly from our medical mind map, it hits 85% accuracy. That 20-point jump, that's not just a better score on a test. In the real world, that represents a huge number of harmful events, of real patient suffering that can now be predicted and totally prevented.
So what we're looking at here is way more than just a technical upgrade. This really signals the beginning of what could be a whole new era of patient safety.
Because when we can finally see and understand these millions of hidden connections in our medical data, we can make the most important shift of all, moving from reacting to harm after it's already happened to proactively stopping it before it ever gets a chance to start. I mean, this is so much more than just clever data science. It's a fundamental reimagining of what patient safety can even mean.
And this whole thing leaves us with a pretty fascinating question to ponder. We've just seen how we can map the connections between drugs, labs, and patients to predict the future. So if we can do that, if we can truly map all the hidden connections in the world of medicine, what else could we predict? What should we connect next?